Now we will learn about how to count independent threads and something called container. So there are many interesting theorems regarding counting independent threads. So we will learn about something called container. So let's consider the following lemma, which gives us an upper bound on graph which satisfies some locally dense condition. So let's say you have integer and R, capital R, data that satisfies the following inequality. Capital R is at least e to the negative beta R times n. If it is an n vertex graph, such that the number of edges inside of X is at least half times data times X squared. So this holds for all sets, vertex set as X of size at least capital R. So if you see a vertex set and there are many edges, so this means it is locally dense. Then we said that there exists a projection of, let's say, C1 to C, say, n choose R, which are all subsets. So this is collection, and each of them are sets, vertex set, that satisfies the following. But do you notice each CI is union of SI and AI, where each AI has a more capital R, and each SI has a most R for each I with between 1 and 2 R. And for every independent set, I of size at least R, there exists I such that its independent set contains Si and is contained in FCI. Okay, so if we know such a collection exists, then what we know? So what do we know? Whenever we have an independent set, it says that it's inside one of them. So each of them are container. It contains independent set. Moreover, whatever independent set you take, it is contained in one of them. So altogether, it contains all the independent sets. And there are not too many of them. In particular, what do you know? For any A, at least R, the number of independent sets of size K in G is at most what? There are n choose r many container, and each of them has the specific SI. So R, so once you choose this I, then we know that this is already in I. And for the rest, you choose from A, which has size m most R. And then there you choose K minus R. So this provides an upper bound on the number of independent sets in a graph, in a given graph G, which satisfy this locally dense condition. So we know, let's prove it. How do you do it? We will use something called Kreitman-Winton algorithm. So we fix ordering V1 to Vn of the vertices, which is called the max degree ordering. So that what does it happen? So Vi has maximum degree in the induced graph, which consists of all the vertices from Pi and later. So how do you generate it? You have G, and then there you choose one vertex with highest maximum degree. You let it be V1. And then you delete it. And then in the remaining, you have a vertex with a highest degree, maximum degree, and you assign it to V2 and delete it and so on. Of course, there are more than one choice of maximum degree, then you choose one of them. This is A ordering. So there could be multiple such ordering, but we choose one of them and then we fix. And then what? Now we consider all possible sets of size R. The S1 to S choose N choose R of G. And we will assign sets A1 to AN choose R. That satisfies the verb property. And what do you do? Let's say you have this U0. So let U0 be the entire vertex set. And we consider this P1, P2, one by one in order. So what do we do? So for given UI, we let UI plus 1 be one of these two. You choose BI. So far you have chosen nothing. So I is 0. And then you choose B1. And then if this B1 is in U0, no, sorry, it's if this BI we let you consider the so BI plus 1 is in F. So let's say fix T. And for given FT, we build AT. So for the fixed one, if this one is in FT, then what we do is we delete the close neighborhood of this bi plus 1 from U. So you delete bi plus 1 and you delete all the neighborhood. And if this one is not in ST, then you simply delete bi plus 1. So you have U0, and you take B1, and then if this is not in ST, then you simply delete B1 from here. And then you see B2, and if this is also not in here, you just delete it. And now B3, this is in here, then you B3, you delete this as well as its neighbor. So this remaining thing is what? U3. You keep to that. You do this until we have considered all bi in this FT. And let say AT is the final value. Okay, what do we know? This FT has R vertices. That means we have done this process, this procedure, R time to get this here at this set. And what do we know? Note that the maximum degree vertex bi, which is chosen above, it has what? Due to this locally dense condition, for whatever x you take, it has this many edges. So every degree is at least beta x. So when you choose this maximum degree, bi from here, what? It has at least beta times n minus I plus 1 neighbors in here. Xi has degree at least the beta of times ui. Ui plus 1 chosen here. Because every time we choose we select this pi plus 1, but set ui, once you delete this remaining thing has size almost it. Because at ui, they shrink by the factor of 1 minus beta. Thus, it becomes size and most what? 1 minus beta to the r times n, because if happen r time, that's almost e to the minus beta r n. And from our condition, this is m mod r. That's what we know that this AT has verified the most high, as we have seen in before. So that shows that this holds. Then now we have to check that the second condition also holds. Great. So let C of t be st linear with AT for each of this t. And for each independent set, I mean, if it assigns M of R, then it must belong to one of Xi. So we consider the independent set of type at least R. Then what first? We claim that there is a T such that this belongs to here, and then this contains here. What we do? We run the Gleichmann-Winston algorithm with I in the place of ST. So instead of ST, we run in this algorithm, but we only stop after consider it R vertices of I. So you do the exactly same thing. So you start from U0, which is the entire thing, and then you consider one by one. And this is in I, then you do that. If this is not in I, you just delete it. You do that, but you don't go till the end. You just stop it after you've done the first option R time. Then what the R vertices considered in I that yields ft or some t, and the remaining set, because exactly those vertices are considered, the corresponding set AT is same. So for this choice of ft and for this choice of R, this algorithm runs exactly the same way, so that the final set is same, and this contains all vertices in the independent set that we have not considered yet, because we only shrink it in the way that this is not in I, then this is deleted, and this is deleted, then all the labeled of Bi plus 1 is also not in I, because I is an independent. So all the remaining vertices are in A sub T. So you know that this holds as desired. So this provides an efficient way to count the number of independent cells in a locally dense graph. And it has many applications. Okay, so one of the applications we can consider. Okay, maybe let's break the video here, and I will consider some applications in next video.